Hello students. Hello and welcome to this video. In this video, we will solve question number 71 to 80 of binomial theorem. The link to download the PDF will be in description. At the end, I will show you how we can download and maintain a copy of the PDF. As well as I will show you my question answer website where you can come and ask questions. So question 71 says that if the coefficients of Rh, R plus 1h and R plus 2h terms in the expansion of 1 plus x to the power n are in AP, show that n square minus n times 4r plus 1 plus 4r square minus 2 is equal to 0. So coefficient of Rh, R plus 1h, R plus 2h terms in the expansion are in AP. So we can write that 2 NCR, that is coefficient of the R plus 1h term, is equal to NCR minus 1 plus NCR plus 1, that is coefficient of R plus 2h term and coefficient of R term. So from this we get 2 upon r times n minus r is equal to 1 upon n minus r times n minus r plus 1 plus 1 upon r times r plus 1, which when you solve you get n square minus n times 4r plus 1 plus 4r square minus r is equal to 0. Question 72 says that if the coefficients of 3 successive terms in the expansion of 1 plus x to the power n are in the ratio 182 is to 84 is to 32, prove that n is equal to 18. So proceeding like previous problem, TR is NCR minus 1, TR plus 1 is equal to NCR, and TR plus 2 is equal to NCR plus 1, where we have taken RH, R plus 1h and R plus 2h term as indicative terms. So we find out the ratio of the coefficients r upon n minus r plus 1 from first two is equal to 13 upon c, and from the last two we have r plus 1 upon n minus r is equal to 14 upon 5. We solve these two equations, we get n is equal to 18. Now we have a series of questions on the expansion 1 plus x to the power n is equal to c0 plus c1 plus c2x square up to cn x to the power n. Here C0 means NC0, C1 means NC1, C2 means NC2, and so on. So 73 one is we have to prove that C1 plus 2 C2 plus 3 C3 up to NCn is equal to n times 2 to the power n minus 1. So here if you see the RH term, it would be R into NCR, okay, is equal to n times n minus 1 CR minus 1. So if you sum this, it will be n times n minus 1 CR minus 1. So take n out, you get n minus 1 C0 plus n minus 1 C1 plus n minus 1 C2 up to n minus 1 C n minus 1, which is equal to n times 1 plus 1 to the power n minus 1. Because if you put x is equal to 1, you will get this one. So you get n times 2 to the power n minus 1. If you are a calculus student and you know calculus, then you can write that 1 plus x to the power n is equal to C0 plus C1x plus C2x and so on up to Cnx to the power n. To differentiate with respect to x, you get n times 1 plus x to the power n minus 1 is equal to C1 plus 2 C2x up to n Cn x to the power n minus 1. Put n is equal to x is equal to 1. You get the required series. Question 74 says that C0 plus 2 C1 plus 3 C2 up to n plus 1 Cn is equal to n plus 2 times 2 raised to the power n minus 1. So here general term is R NCR minus 1, that is R minus 1 NCR minus 1 plus NCR minus 1. Now this we can write as n times n minus 1 CR minus 2 plus NCR minus 1, because R minus 1 NCR minus 1 is equal to NC n minus 1 CR minus 2. So from this we sum the series from R is equal to 0 to n. We get C0 plus 2C1, I is equal to 1 to n plus 1 actually. C0 plus 2C1 plus 3C2 n plus 1 Cn is equal to sigma PR R is equal to 1 to n plus 1. So we sum these two, and the sum would be n times n minus 1 c0 plus n minus 1 c1 up to n minus 1 c n minus 1 and c0 nc0 plus nc1 up to ncn. So this we have already proven to be n times 2 to the power n minus 1 plus this would be 2 to the power n because in 1 plus x to the power n we put x is equal to 1. So the entire sum is 2 to the power n minus 1 and times n plus 2. Now the calculus method is we have this series, we multiply with x, we get c0x plus c1x square plus c2x cube up to cnxn. Now we differentiate with respect to x, we get 1 plus x to the power n plus nx 1 plus x to the power n is equal to c0 plus 2c1x plus 3c2x square and so on. Now we put x is equal to 1 and we get c0 plus 2c1 plus 3c2 up to n plus 1 cn is equal to 2 to the power n minus 1 times n plus 2. Question 75 says that c0 plus 3c1 plus 5c2 up to 2n plus 1 cn is equal to n plus 1 to raised in power n. So TR is 2r minus 1 CR minus 1, that is 2 times r minus 1 plus 1 CR minus 1, which is equal to 2 times r minus 1 CR minus 1 plus CR minus 1, which is equal to 2 times n minus 1 CR minus 2 plus CR minus 1, because r minus 1 CR minus 2 is equal to n times n minus 1 CR minus 2. So we take the sum where r is equal to 1 to n plus 1 sigma TR, and we do the summation, we get this as the result. Now for the calculus method, we put x is equal to x square and multiply with x. So we get c0x plus c1x cube plus c2x5 up to cn x to the power 2n plus 1. And left hand side becomes x times 1 plus x square to the power n. We differentiate both sides with x, we get 1 plus x square to the power n plus 2x square times n times 1 plus x square to the power n minus 1 is equal to c0 plus c1 times 3x square plus c2 times 5x to the power 4 up to cn at 2n plus 1 x to the power 2n plus 1. Now we put x is equal to 1, we get the desired series. Question 76 says that we have to prove that c1 minus 2 c2 plus 3 c3 minus 4 c4 up to minus 1 to the power n times cn is equal to 0. So TR here is minus 1 to the power r minus 1 r c n minus r, or n cr, which is equal to minus 1 to the power r minus 1 n times n minus 1 c r minus 1. So we put it for in sigma for I is equal to 1 to n. We get sigma n times sigma r is equal to 1 to n minus 1 to the power r minus 1 c r minus 1. Now we substitute the values for r, we get n times n minus 1 c0 minus n minus 1 c1 plus n minus 1 c2 up to minus 1 to the power n minus 1 n minus 1 cr minus 1, which is equal to n times 1 minus 1 to the power n minus 1 is equal to 0. Now the calculus method is we have this expansion, we differentiate both sides with x. So we get n times 1 plus x to the power n minus 1 c1 plus 2x c2 plus 3x square c3 up to n x to the power n minus 1 cn. Now we substitute x is equal to minus 1, we get n times 1 minus 1 to the power n minus 1 is equal to the required series. Question 77 says that we have to prove that c0 plus c1 by 2 plus c2 by 3 and so on up to cn upon n plus 1 is equal to 2 to the power n plus 1 minus 1 upon n plus 1. So here the ith term is ncr minus 1 upon r. Now we sum this general term from r is equal to 1 to n plus 1. We get sigma r is equal to 1 to n plus 1 cr upon r n plus 1, because ncr minus 1 upon r is equal to n plus 1 cr upon n plus 1. Now we add this, you need to add and subtract n plus 1 c0 on both sides, and then you will have the required sum. Now the second method is that you integrate the standard expansion within limits 0 to 1 and you will get the required series. Question 78 says that we have to show that C0 minus C1 upon 2 plus C3 upon 3 minus so on plus minus 1 to the power n Cn upon n plus 1 is equal to 1 upon n plus 1. So here general term is minus 1 to the power r ncr minus 1 upon r, which we can write as minus 1 to the power r minus 1 n plus 1 cr upon n plus 1. And then we substitute uh, x is equal to minus 1, right? And then you will finally sum this, and it will be equal to minus of minus 1 minus 1 to the power n plus 1 plus n plus 1 C0, which is equal to 1 upon n plus 1. For the calculus technique, we have to integrate within the limits 0 to minus 1. If you integrate it, you will have the required sum. Question 79 says that you have to prove that C1 upon 2 plus C3 upon 4 plus C5 upon 6 is equal to 2 to the power n minus 1 upon n plus 1. So here general term is nc2r minus 1 upon 2r is equal to n plus 1 c2r upon n plus 1. So C1 upon 2 plus C3 upon 4 plus C5 upon 6 and so on will be equal to 1 upon n plus 1 sigma n plus 1 C2R. Now here R is equal to 1 to n. Okay. So not 1 to n, it is an indefinite series. So we sum this 1 upon n plus 1 C2 plus n plus 1 C4 plus n plus 1 C6 and so on. Now this is equal to 2 to the power n minus 1. So we have 2 to the power n minus 1 upon n plus 1. For the calculus method, we add the result of last two problems to arrive at the required sum. Now we come to the last question of this set. We have 2 times C0 plus 2 square C1 upon 2 plus 2 cube times C2 upon 3 up to 2 to the power n plus 1 Cn upon n plus 1 is equal to 3 to the power n plus 1 minus 1 upon n plus 1. So general term is 2 to the power r ncr minus 1 upon r is equal to 2 to the power r n plus 1 cr upon n plus 1. So we sum from r is equal to 1 to n plus 1. We have the left hand side, and that right hand side will become 1 upon n plus 1 cr times 2 to the power r, which we sum, and this would be 1 plus 2 to the power n plus 1. And we have to add and subtract n plus 1 c0 to this sum. You add and subtract. So this minus 1 is coming from there. And that's how we have 3 to the power n plus 1 minus 1 upon n plus 1. So in the expansion, it is 1 plus 2 to the power n plus 1. Now for the calculus method, we integrate between the limits 0 and 2 to have the desired sum. Okay. So with this, we come to the end of this set. Now let me show you my website. You can come to astrolocker.org, click on link 2, 3 and 4 to download algebra, trigonometry and coordinate geometry books. Note that the downloaded PDF will not have dates, so you need to add dates to the PDF. And after 15-30 days, you come and check whether a new version has been released. And if a new version has been released, then you can download again and update the date. I cannot put the date in the PDF because that will make all existing links invalid. YouTube links, or someone has shared the link, it will become invalid. Note that there are lots of typing mistakes, so read carefully. Okay? I have nobody to proofread this, so there are lots of problems. Now, if you want to ask questions, you can click the X link. You will come to this website, kundika.astrolocker.org, and here you can make a login and ask questions. There are standard tags done for you: algebra, calculus, coordinate geometry, geometry, probability, mathematics and trigonometry. So you can use these tags to ask a question. If these tags do not match, just give mathematics and that should be enough. So with this, I will end this video here, and I hope that you are finding this series of playlists useful and informative. Thanks a lot for watching the video. I'll see you in the next one. Till then, stay curious, keep learning, and most importantly, enjoy.